Hello and welcome to these video notes on turning velocity versus time graphs into position and acceleration versus time graphs. These graphs will be quantitative, meaning we will have numbers associated with them, and they will involve acceleration. Before we begin with our examples, I think it's worth spending some time looking at a velocity versus time graph and making sure that we understand what's going on in the graph before we just start converting plots. So, remember on the y-axis we have velocity now, which is how fast you're moving in a given direction, and obviously we have time in the x direction. So the first thing we need to do is be able to break this up into chunks based on different motion. At first glance, we end up with 4 different types of motion here. That's what you would initially think. But with velocity versus time graphs, we really have to think about what is happening with respect to the x-axis. So this section right here, the one that I've colored in maize and blue, sorry, ends up being 2 chunks. And we'll see why that is here in a second. So we've got 5 different areas. We've got the purple area, which is sort of where we're going to start. We've got the red area, which is second. We've got our blue area, which is third, right there. We've got our yellow area, which is fourth, and we've got our green area, which is fifth. So a simple looking graph is actually going to have 5 different regions. So to start analyzing this kind of in order, I'm going to zoom in a little bit here, and we're just going to describe each of these sections with words. That way when we get to our section on converting, we kind of know how to read these and make sure that we're really sound with that ability. Okay, so our purple section starts with the velocity right here at 0. So we start off with a velocity of 0, and what that means is the object starts for a moment at rest. You then notice that the velocity goes from 0 to 5 to 10. So the velocity is going from rest to a velocity of 10 meters per second, which means that our object is accelerating. Obviously, it's accelerating kind of in multiple spots here, but what I mean by accelerating in particular is it's speeding up, and it's becoming more and more positive with its velocity. So it's speeding up, and that means it's speeding up in the positive direction. We're getting a more and more positive velocity, so we're getting 2 things here. We're speeding up, meaning that the speed is increasing, we're getting a larger and larger number, and it's speeding up in the positive direction. The number is more and more positive. At the point at which we turn to red here, we notice that this becomes flat. At the time it becomes flat, we know that flat areas of this graph mean constant velocity. And the number is going to be how fast it's moving. So we have a constant velocity at 10 meters per second. So this object sort of has started off at rest. If we kind of want to picture this already as sort of an x versus t graph, it is sort of started at rest, it is sort of sped up, and eventually it hits a clip of 10 meters per second at a constant velocity, which means this slope in this little red section of the graph would be 10 meters per second. So that's sort of what we've done so far. Then we hit the blue part. Now the blue part is sort of the opposite of the purple part. We start with the velocity of 10 meters per second at the start, and we are going to 0. So equals 0 meters per second. So if you're traveling 10 meters per second, and then eventually you hit 0 meters per second, that is a deceleration, or a slow down. Now, that means we will have a negative acceleration because it's slowing down, but we are still moving in the positive direction, right? Nothing has changed here in terms of the direction we're moving. We're still up here in the positive region of the graph. It just means that we're slowing down to a stop at the end. Okay, so if we're thinking again of what that would kind of do to a position versus time graph that I'm sort of sketching up here in the top corner, it would start to slow down. Okay, the object would eventually come to a stop at the point right here. I'm going to mark it with a nice, like a little star. That moment that sort of happens right here in between, right there, is again a momentary stop. Then what we end up with is this yellow section. Now the yellow section, we start at this stop, v equals 0 meters per second. And all of a sudden we're going to a velocity of equal to negative 10 meters per second. So notice by the time we go from 0 and we move along this yellow line, we are now traveling at negative 10 meters per second. So what this means is that we're accelerating again, or we're speeding up. But this time we're doing so in the negative direction. So the other thing that kind of happened here at this stop point is not only did it stop, but it also, and just because I don't have a lot of room there, it turned at that spot. So anytime you have this graph and it crosses the axis, the x-axis to be specific, anytime it crosses the x-axis, that will be a turning spot, meaning that the object has slowed to a stop and then it has reversed its direction, meaning it is now going in the negative direction through the yellow spot. That is why it is really important to break this section up into blue and yellow, because the object turns in the middle there. It doesn't look like it, but it goes from having a slowing velocity to a stop, and then it takes off in the negative direction. So that's why that is super important to break that up into two chunks. The last section here is again a nice constant velocity at negative 10 meters per second. So the object has sped up and eventually reaches negative 10 meters per second in the negative direction. So to add those two sections onto the little position versus time graph, it starts to speed up in the negative direction and eventually it's linear. And that was a little probably more dramatic than it needed to be, so I'll just shorten it there. But that's essentially what it means. The object is turned around at the little star. I'm going to put the star in my position versus time graph right there. And it has taken off in the negative direction. So, one last time, and then we'll move on to some examples here of how to convert this plot. But the object has started at rest, it is sped up, eventually reaching a constant positive velocity of 10 meters per second. It then starts to slow back down, coming to a stop at 4 seconds. It then starts to speed back up in the negative direction, eventually reaching negative 10 meters per second, and then it travels at a constant velocity for at negative 10 meters per second for that last 5 to 6 second area. So again, pretty seemingly quote-unquote simple graph to look at, but it's got a lot of complexity. And the biggest thing we have to remember to do is really analyze this through velocity versus time, the lens of velocity versus time. Because if you analyze this as a position versus time graph, or think about it that way, you're going to get things that are totally off. Remember, what we're going to need to do here is use the area under these shapes in order to find our displacement and go to an actual position versus time graph. So we're going to be doing that in our next couple slides, finding the areas under these shapes, and that will get us our position versus time graphs, and then we will use the slopes to find acceleration versus time graphs. So let's take a look at two examples of doing that. Okay. So here's our first example of a pretty, I guess, simple velocity versus time graph, and we're going to turn this into an acceleration versus time graph and a position versus time graph. Now, I'm going to take the same approach that I did on the previous slide, and I'm going to first I'm going to zoom in a little, just because it's going to be kind of annoying to try and highlight and draw on this thing with it being so small. So we've got, again, two chunks of this graph. Don't know why I can't trace it there. That's as good as it's going to get. We've got two chunks again. And anytime we have a velocity versus time graph, remember that that spot right here is going to be important because that indicates, again, a turning spot. So anytime that this crosses the x-axis, it's going to turn. So again, to kind of describe this a little bit with words first, we have an object that is starting at v equals 4 meters per second, and then it's going to a velocity of 0 meters per second. So what this tells me is that it's slowing down. Now, again, the direction here is it's on the positive part of the graph, meaning that it starts at a positive 4 meters per second and it goes to 0. So again, it's slowing down, but the direction is still positive. That's important. It is not going in the negative direction until it turns at this turning spot, and then it is speeding up. It's going from 0 meters per second to negative 6 meters per second, and that is speeding up in the negative direction. So this is kind of like the last portion of the graph on the previous slide. And it's a real nice example of, again, that importance of turning point at the x-axis. So, to turn this into an acceleration versus time graph, it's actually not that difficult. All we really need to do is find the slope of this graph and put it over here. Because remember, the slope, meters per second divided by seconds, is going to be meters per second squared, or acceleration. So, I'm going to do this in the two chunks we have on the graph, just because even though the slope here looks like it's consistent, it's good practice to do each individual chunk separately in case you have an example where the slope changes. So, in the blue chunk here, we're going to do, again, rise over run. So the rise is initial, which final minus initial, which would be 0 minus 4, divided by the time change, which is 4 minus 0. Now, the 0 minus 4 part is important here because that is going to give us a negative number. It's going to give us a negative number because, again, slowing down equals negative acceleration. And that's important. We have a negative slope here, so this number should be negative, meaning that it is slowing down. So our first chunk here is going to be at negative 1 meters per second squared. Now this grid has a lot of boxes, so I'm just going to be really dramatic about it and put negative 1 all the way down here, just sort of on a whim. 1, 2, 3, and this happens for the first 4 seconds, which would be right there. And I'm going to draw my line going across for the blue portion of the graph. 1, 2, 3, 4. There it is right there at negative 1. So, again, we have a linear line on the V versus T and a flat line or horizontal line at A versus T. Remember, in this class, the slope of an A versus T graph will always equal 0, meaning that this will always be horizontal. That's important. Alright, now to do the purple part, we are going from final minus initial, which would be negative 6, minus 0, over 10 minus 4. 6 minus 0 is negative 6, divided by 10 minus 4, which is 6. And that gets us the same thing. Like I said, it looks like it's pretty consistent through there. So even though, sorry, can't talk and draw at the same time. Even though the motion here changes, the acceleration ultimately stays the same. Meaning that the object is slowing down in the negative direction, or slowing down, which means a negative acceleration, in the positive direction, and then the speed up in the negative direction is also happening at the same rate, which is kind of weird, and that tends to be where people get kind of stuck with this idea of slowing down in the positive and speeding up in the negative, ultimately looking the same. But again, even at the most simple kind of thought here is that, remember, This is slope. So whatever the slope here is, you just put it there. So, you know, in both cases of this, you know, slowing down and then speeding up in the negative, the slope is -1. So that's just what it's going to look like. And there it is. Now, that's pretty easy because slope's pretty simple to deal with. Going in the other direction, though, takes just a smidge more effort because remember we have to use area underneath these shapes or between these shapes and the x-axis in order to find the displacement. Now, before I go to do this, I think it's probably pretty smart to think about what this shape is going to look like, just kind of qualitatively. We're going to start with it traveling at about 4 meters per second, and then it's going to slow down. So that's the blue part. I'm going to draw it in blue. We start with about 4, and then it slows down. We have that turning point, which we said happens right there at 4 seconds. And then it starts to speed up in the negative direction. So we're going to get a graph that kind of has this sort of parabolic arc shape to it. At least that's what we should see. The big question is, what are the distances traveled in this time? Like, how much did it go here, and how much does it go here? So we kind of know how those shapes play out. Again, I'm going to do this with area. So under this triangle right here is going to be the amount of distance the object travels during the slowdown part. So I'm going to come down here. So area of a triangle is going to be 1/2 base times height, or 1/2 of 4 times 4. 4 times 4 is 16, times half is 8 meters. So we're going to say that the object starts at 0, make it nice and easy on ourselves. And we're going to say that during its time between 1, 2, 3, 0 and 4 seconds, that it travels 8 meters. And again, it's slowing down. It starts at 4, so it starts sort of with a nice slope, and it's flattening out over time. So we know that between, we've got a point at 4 and 8 right there. We've got a point at 0, 0, and we know this shape. So it's going to look kind of like that. So there's our first part, represented by that triangle. Again, we've got that slowing down arc going from a slope of about 4 to a slope of about 0. We've got the turning point, which will be right up here. And then we're going to do the second part of the graph, which is again a triangle. It's a triangle down here. Now, this triangle is going to be negative when we do this because it's got a negative height. And that's going to be important because then that's going to give us our displacement from 8 meters. So really important that we take that negative into account. So the area of our second triangle, 1/2 base times height. The base is 6. The height is -6. 6 times 6 is 36, times 1/2 is -18 meters. So what that tells me is that starting at 8, we then travel -18 meters from 8. So what that tells me is the object is going to start at rest 4, 5, 6, 7, 8, 9, 10. It is going to then arc downwards, eventually changing 18 in this direction. Now, some simple math will tell you that that will end up meaning that our object will end at -10. 2, 4, 6, 8, 10. -10 is right there. So the graph will have a point at 10, -10, right there. And it's going to have that sort of arc from no motion to velocity in the negative direction. So we're going to have something that looks kind of like that. Not perfect, but it has the right shape. So that's what that's going to look like. It again starts with the velocity up here of 0. Velocity is 0. And then eventually it has a velocity of negative, -6, which is down there, which is right there. So there's our shape, and it kind of matches up with what we predicted, and it has numbers, and we used area. Sweet. So there it is. there is our first example, how to go from a velocity versus time graph using slope to an acceleration versus time graph, and using area to go back to a position versus time graph. So yeah, let's do a slightly more complicated example. Okay, so in this problem, we have a slightly more complicated graph. Fortunately, we've already sort of walked through one of these, so we kind of know the rules of the road now. So we're going to just kind of hop in. I'm going to kind of outline this. First, we have a velocity going from 0 to 3 meters per second, which is a speed up in the positive direction. Then we have this section of constant velocity motion here in the middle. Then we have a velocity, we're going from 3 back to 0, which is a slowdown in the positive direction. And then we've got this section here, which the velocity is holding at 0, which means it is at rest. It is not moving. So, with that being said, let's get some slopes here and plot our acceleration versus time graph. So, our first section, we have a rise over run of 3 minus 0 over 6 minus 0, which comes out to be a positive 0.5 meters per second squared. That is supposed to come out positive because we ended up with a nice positive slope. And this happens for the first 6 seconds of motion. So that would be like right around there. So we have a positive, nice acceleration right there. Our second section, if we were to do the math, would get us 0 meters per second squared because it has no rise. The velocity is not changing. So that is going to ultimately be pretty much the same the entire time. It is not going to accelerate. 6, 8, 10, 12, 14, 16, 18. I apologize. Can't count and talk at the same time. So that has 0 acceleration, meaning that the object is at a constant velocity, and our acceleration there is 0. So it is along the x-axis. Our third section, we're going to do the same thing. Now here we're going to have a negative number, obviously, because the slope is negative. Our final velocity is 0 minus 3, which is our starting velocity, or whatever the hell that number was. There we go, a little bit nicer looking. And this is happening between 19 and 18 seconds. So we end up with negative 3 meters per second squared there, or negative 3 divided by 1. So that's going to be obviously a pretty dramatic stop compared to how we at least sped up. Pretty dramatic down here on the graph as well. Don't know why I can't draw the number 3 today. So then we end up with a little line right here between the 18th second and the 19th second. And then at the end we have, again, any spot where there's no slope is going to be an acceleration of 0, and if you're not moving in particular, that's definitely going to be 0. So there's our graph. We've got our 2 accelerated areas, the blue and the green, and we've got 2 constant areas in the purple and yellow. It is also worth noting that we're not going to do this in this video, but we could go back using the area from the acceleration versus time graph to in fact find the velocity versus time graph, just like we can do with the velocity versus time graph and the position versus time graph. So, to now go from velocity to position, this should be pretty simple. Again, we're going to use both the shapes and the numbers here to kind of guide us. So we're going to start with the blue section of the graph, which is, again, a triangle like we just did. There it is. 1/2 base times height. I'm going to do it up here. Area is 1/2 base height. And for the blue section, it would be 1/2 of 3 times 6. So 3 times 6 is 18, times 1/2 is 9 meters. The object is going from rest to this 9 meters. So we know that it's going to start with no slope and eventually have a decent slope. So it's going to kind of look like that, just as sort of a side note. I'm going to label my axes. 2, 4, 6 is right there. And because it's going to continue forward for a while through the purple and green sections, I really need to be careful with how I'm going to deal with my y-axis here. So even though it's probably not going to be super pretty, I'm going to go up by tens. And again, that's not going to be super pretty, but it's going to have to be what works here, just because we're going to have some big numbers to contend with. So 10, 20, 30, 40, 50, 60, 70. So our first section, we're going to end up after 6 sections at about 9, which is going to be right around here, and it's speeding up. That's what we got for our first section. We've got a nice slow speed up towards 9 meters. And I'm going to try and highlight that. No, don't like that. Never mind. See if I can make this just a little more noticeable on the graph. There it goes. That's okay. Alright, so now we're going to do our second section, which is the purple square, or rectangle rather, right there. This is nice to deal with because the area is just base times height, or velocity times time. Physics. Remember, it's in there still. So this is going to be 12 seconds times 3 meters per second, or 36 meters. Which means between 6 and 8, 10, 12, 14, 16, 18, which is right there, we're going to travel an additional 36. So 36 plus 9 is going to give us a total of 45 meters at this point. So that means right smack in between 40 and 50 on my graph. So I'm going to zoom in again just so we can get a spot that looks right. So between 40 and 50 is going to be right around here. 18 is going to be right around there. So we've got a spot right there on my graph. Going to get rid of those just to make it look a little neater. And remember, in this section, we're moving at a constant velocity, so the line should be relatively straight. It's not going to be perfect here because I'm just not a good artist and I'm not very good at drawing nice, pretty lines. But you get the point. It's not curved, it's relatively linear. There it is. Okay? Now, our third section is going to be our slowdown section. Again, we're going to do area. Now, this triangle is very, very small and kind of narrow. So we're going to get 1/2 base, which is just 1, times height, which is a -3. Or a +3, I apologize. We're above the x-axis, so it's positive. Guess this video is starting to get to me, right? So 3 times 1 times 1/2 is only a +1.5, which is a very, very, very small number, especially on the scale of this thing. So we're going to essentially, in this 1 second between 18 and 19, right in this 1 second, we are going to come to a complete stop. And it's going to look kind of like that. It's just going to like immediately plateau and come to a stop dramatically over the course of 1.5 meters, which on a 10-meter scale like this is pretty much inconsequential almost. And then for our last chunk of the graph, the object is at rest, which is nice because that means when there's no area, it's not moving at all. And that means we can draw a nice flat line right here. So we're going to go, whoops, not over our green though. And we got a nice flat line after this very pretty and dramatic arc. Alright, so there we go. We did, again, area to get from the velocity versus time graph to the position versus time graph, and slopes from the velocity to the acceleration. I'm hoping that this video helped provide some more examples for you. And, yeah, have a great day. Hopefully this helped.